In the previous lecture, we discovered that almost all numbers are irrational numbers. Despite this reality, here we'll show that the very sparse collection of rational numbers is spread all over the number line. Said mathematically, the rationals form a dense collection of numbers within the real numbers. We'll then generalize the collection of rational numbers and arrive at the world of algebraic numbers. Even though we'll see this new collection of numbers is much more interesting and exotic than the humdrum rational numbers, these algebraic numbers possess a rich algebraic structure that actually resembles the structure possessed by the rational numbers. We'll then transcend the algebraic numbers and wonder if there are numbers that are not algebraic. These enigmatic numbers, called transcendental numbers, were not even known to exist until the year 1844. It was in that year that Joseph Liouville discovered a remarkable theorem connecting rational and algebraic numbers. His result offered humankind, for the first time, mathematical proof that transcendental numbers do indeed exist. Well, in order to inspire his groundbreaking work on transcendence, we'll return to the simpler issue of irrationality and discover the corresponding result in that context. We'll then be ready to appreciate Liouville's remarkable result that launched an entire field known today as transcendental number theory. We'll then close this lecture by highlighting a number of advances and lingering open questions in this relatively new field of study. Well, let's recall from the last lecture that the rational numbers are precisely those real numbers with decimal expansions that eventually become periodic. The irrational numbers, therefore, are precisely those values having non-repeating decimal expansions. Using this fact, we concluded that in some sense that can be mathematically made precise, there are more irrational numbers than rational. Well, despite this dearth of rational numbers, we'll now discover that any irrational number can be approximated as closely as we wish by the less common rational numbers. Just by truncating the decimal expansion of an irrational number, we can find a very close rational approximation. For example, if we look at the decimal expansion for the square root of 2, we'd see 1.4142135, and it goes on for forever. And if we just truncate this after the second 1 that we see, then we'd have the decimal expansion 1.41421, which equals 141,421 over 100,000, which is obviously a fraction. And notice that it's very close to the square root of 2. If we subtract that rational from the square root of 2, then we see the distance, and that tiny distance is actually a tiny number, which is 0.000035, and so on. In fact, we're able to get as close as we wish to any irrational number by a rational one. Well, we can also approximate as closely as we want any rational number by a different rational number. For example, recall that a third equals 0.33333, repeating forever. And the truncation 0.333, which equals 333 over 1,000, is a rational number different from 1/3, but the difference between them, the distance, if you will, between them, is a very tiny value, 0.000333 forever, a very small number indeed. Thus, we conclude that given any two different real numbers, x and y, we can always find a rational number in between them. Well, this fact shows us that the rationals are spread throughout the number line. And we say, more formally, that the rationals are dense in the real numbers. that whenever you're standing, any point on the number line and you wiggle a little bit, you're going to be bound to hit rational numbers. Well, it's a great challenge for us to reconcile these two opposing sounding notions. On the one hand, the probability of randomly picking a rational number is 0%, while on the other hand, the rational numbers are essentially everywhere. Well, these facts do coexist without contradiction, and if nothing else, they highlight the incredible subtlety within the universe of number. Well, let's now extend our field of vision and generalize the rational numbers. We begin by noticing that any rational number, say for example 3/5, is a solution to a linear equation. In this case, 5 times x minus 3 equals 0. And let's just check that if we let x equal 3/5, then we see 3/5 times 5 is 3. 3 minus 3 is 0. It satisfies that linear equation. Well, in this way, we can view the collection of rational numbers as the collection of all solutions to equations of the form s times x minus r equals 0, where r and s are any given integers and s is not 0. In this case, the solution to this generic equation would be x equals r over s, and notice that indeed is a rational number. Well, if we now consider slightly more complicated equations, those that involve, let's say, x squares, then we actually find equations such as x squared minus 2 equals 0, which has solutions positive or negative square root of 2. Or an equation like x squared plus 1 equals 0, which has the solutions positive, negative I, the imaginary number square root of negative 1. Or even we can consider x squared minus x minus 1 equals 0, which we saw in several other lectures, has the solution of the golden ratio and its conjugate, 1 plus or minus the square root of 5 all over 2. More generally, any sum of x's raised to natural number powers that can be multiplied by integers, added together, and then set equal to 0 is called a polynomial equation with integer coefficients. So, for example, 3x to the 4th power minus 9 times x cubed plus 17 times x minus 6 equals 0 is a polynomial with integer coefficients because the numbers multiplying the x's are integers. And similarly, even something as crazy as 4 times x to the 10,000 power plus 27 equals 0 is another such example. Well, these equations always have solutions. In fact, the number of solutions is equal to the highest power that we see on the unknown x. Now, in practice, it's extremely challenging to actually find those solutions, even though we know those solutions do indeed exist. Well, if we now identify and define the set of algebraic numbers, we define them to be, in fact, the collection of all solutions to any polynomial equation having integer coefficients. For instance, the square root of 2, I, and the golden ratio are all examples of algebraic numbers. Since these numbers are solutions to quadratic equations, equations having the highest x power equal to 2, we say these are algebraic of degree 2. The 2 telling us, the degree telling us that, in fact, that's the highest power we see on the x's. The number cube root of 5 is an algebraic number of degree 3, since it's the solution to a cubic equation x cubed minus 5 equals 0. In fact, we've remarked earlier that every rational number is an example of an algebraic number. In particular, the rational numbers are algebraic of degree 1 because they're solutions to linear equations. The x appears to the 1st power. Well, more exotic algebraic numbers can be created by combining integers with the operations of addition, subtraction, multiplication, division, exponentiation, and taking roots. So, for example, the cube root of 1 minus the square root of 71 all divided by the fifth root of 29 plus 31, all raised the denominator to the eighth power, is an algebraic number. We can actually find a crazy polynomial out there with integer coefficients for which this wild number is a solution. But let's not actually do that. Well, given that we can create such extremely complicated numbers, we now wonder if we can build all numbers in this manner. In other words, we ask, are all numbers algebraic numbers? That is, are all numbers solutions to polynomial equations with integer coefficients? Well, this question parallels our earlier discussion about whether all numbers are rational. When we considered this conundrum, we discovered that, in fact, not all numbers are rational. Irrational numbers, in fact, exist. So, do non-algebraic numbers exist? If a number is not algebraic, let's call it transcendental. In other words, a number is transcendental if it is not a solution to any polynomial equation having integer coefficients. So, the daunting question we now face is, do transcendental numbers exist? Well, for hundreds of years, people believed that pi is an example of a transcendental number, but no one was able to prove it. It's extremely difficult to prove a number is transcendental. For one thing, transcendence is defined by what it's not. In other words, what we have to do is, to prove a number is transcendental, we have to actually show that it's not a solution to all the infinitely many different polynomial equations out there with integer coefficients, something that's not very practical to do in practice. Perhaps not surprisingly, one of the greatest open questions in mathematics right up into the 19th century was, do transcendental numbers even exist? Well, the answer was finally given by the great French mathematician Joseph Liouville in 1844 in a most elegant and supremely beautiful theorem. Liouville's father, by the way, as an aside, was actually a captain in Napoleon's army. So he came from interesting stock. Well, to inspire Liouville's seminal work, we momentarily leave the subtle dichotomy of algebraic versus transcendental numbers and return back to the somewhat more familiar and grounded issue of rational versus irrational numbers. Let's recall that the rational numbers are dense within the real numbers. In particular, if we are given any fraction at all, let's say 2/3, we can find another rational number that is as close to 2/3 as we wish. However, we'll now show that those rational numbers that are extremely close to the original fraction must have enormous denominators. For example, let's suppose that we found a rational number p over q that's different from 2/3, but extremely close to 2/3. Say just a little bit smaller than 2/3, and for example, 2/3 minus this rational p over q is in fact smaller than 1 over 3 million. So the difference between 2/3 and this approximation p over q is within 1/3 millionth. That's really, really small. Well, if we combine the fractions we see, getting a common denominator, we would see that 2 times q minus 3 times p, all divided by 3q, is the difference of those rational numbers. And since p over q is different from 2/3, it follows that that numerator, 2 times q minus 3p, is a positive integer. Hence, it must be greater than or equal to 1. Well, so we conclude that this difference, 2/3 minus p over q, is going to be greater than or maybe equal to just 1 over 3 times q, and we throw away that large numerator, replacing it by the smaller 1. On the other hand, we've already assumed that that difference is actually smaller than 1 over 3 million. Well, this implies that 3 million is smaller than 3q by cross-multiplying, if you will. Or if we divide both sides by 3, we discover that 1 million is actually smaller than q. In other words, the denominator that's really close to 2/3 must exceed 1 million. Well, notice that this is exactly what we were trying to accomplish. Any rational number really, really close to 2/3 has a very, very large denominator. So, in fact, we can actually apply the exact same argument with a fraction p over q that's just a little bit bigger than 2/3 rather than smaller, and we get the same kind of result. And we could repeat our argument just using p over q minus 2/3 rather than the other way around. Or more generally, we could actually use the absolute value to measure the distance. And we'd say the absolute value of 2/3 minus p over q, and then we don't worry about positive or negative. We always know that's going to be greater than or equal to 0. Well, this has the attractive feature that we don't have to worry about who's bigger and who's smaller, or who's on first or whatever. We just need to take a look at the distance between those two numbers, and the absolute value allows us to find that distance. Well, this principle can actually be generalized to show that even though the rationals are dense in the real numbers, rational numbers in some peculiar sense repel other rational numbers having small denominators. This result can be stated as a theorem, and the theorem would read, let r over s be a fixed fraction. Then we can find a positive constant number, let's call it c, such that for every single rational number p over q that's not equal to r over s, the distance between r over s and p over q is always going to be bigger than this constant c divided by the denominator of the approximate q. In other words, we'd say c divided by q is less than the absolute value of r over s minus p over q. Namely, if you want to approximate the rational r over s by another rational p over q, they can't get too close together. They can get no closer than a constant divided by the denominator q. In the previous example, by the way, we saw that this constant c was 1/3, because we had 1 over 3 times q in that example with 2/3 before. Now, for those of you who are interested in the details, to prove this theorem, we will follow the exact same footsteps of our previous example. But now we'll just replace the 2/3 by the unknown given fraction r over s. But the steps will remain the same. I'll outline them pretty quickly for us just to see that, in fact, nothing new is going on. So first, let's notice that since p over q, our rational that's approximating r over s, is not equal to r over s, we're picking a different rational number, then when I combine the difference and see p times s minus r times q, all divided by q times s, that fraction is not equal to 0, because the rationals are different. So again, that numerator is a number in absolute value that's greater than or equal to 1. And so we see that 1 over s times q is smaller than the difference between r over s minus and p over q. So r over s minus p over q in absolute value. Or equivalently, I could write this a little bit more cryptically as the constant c over q is smaller than the absolute value of r over s minus p over q, where the constant c is specified to be 1 over s. And this actually establishes the theorem in general. But you can see it's the exact same principle as previously seen in the example. Well, our theorem, which by the way I admit is a little bit technical, so it's a little bit deeper, but we're trying to get to some deeper number theory here. Our theorem can be summarized as follows. If we're given a rational number, then any other rational numbers that are very close to the given fraction must have a relatively large denominator. That's the moral of the theorem. That's all I want us to get out of it. Now, put on its head, we note that this result is equivalent to the following statement. If we have a number alpha for which we can find an endless list of rational numbers approaching alpha, each having a relatively small denominator, then alpha cannot be a rational number. In other words, alpha must be irrational. Because remember, the rational numbers repel other rationals with small denominators. So if you found a number that has a lot of rationals nearby having small denominators, then in fact, that number can't itself be rational. It must be irrational. For example, if we consider the number 1.100100001, and then 6 zeros and a 1, and then 8 zeros and a 1, and then 10 zeros and a 1, and so forth, continuing in this fashion, then we find an endless list of amazingly good rational approximations having relatively small denominators. For example, notice that 1.1, which equals 11 over 10, is very close to our number. The difference is approximately 0.0001, or 1/10,000th. Well, so with a denominator of just 10, we're nearly 1/10,000th away from our original number. That's really close for a very tiny denominator, approximate. Well, since we have infinitely many such amazing rational approximations relative to the size of their denominators, we can actually apply our theorem to conclude that the original number must be, in fact, irrational. Of course, we can confirm this number is indeed irrational since we can see that its decimal expansion is non-repeating. We constantly have more and more zeros sandwiched between those two ones, in fact, always an ever-growing even number of zeros. Now, as an aside, it's this very theorem that allows us to prove that Euler's special number E, 2.71, that we saw actually in the previous lecture, is indeed irrational. So this theorem actually is quite useful. It allowed us to prove that E is in fact an irrational number. So our theorem can now be extended to algebraic numbers, and this was the amazing insight of Joseph Liouville. Liouville generalized our result involving rational numbers to a result involving algebraic numbers. So let's see how this is going to work. Let's let alpha be an algebraic number having degree d, which means that if you look at the polynomial for which alpha is a solution, the highest power on x is d. Then Liouville proved that there exists a positive number, some constant called c, such that for all rational numbers p over q that are not equal to alpha, we have that the distance from alpha to p over q, or the absolute value of alpha minus p over q, is always greater than this constant divided by q to the d. And this result is in fact now known as Liouville's theorem. Now notice that Liouville's theorem agrees with our earlier result if alpha equals the rational r over s, because in this case the degree is 1, and so we see in that lower bound in our inequality, constant over q to the d would be now c divided by q to the 1, which was the result we had. Well, just as we saw before, this result implies that if alpha is an algebraic number, then any rational number p over q that's relatively close to alpha must have a relatively large denominator q, by the exact same reasoning. Equivalently, we see that if we found an endless list of rational numbers approaching alpha at an amazingly fast rate compared to their relatively small denominators, then alpha cannot be algebraic. The theorem wouldn't tolerate it. In other words, alpha must be transcendental. And I must say that, in fact, Liouville's theorem is my absolute favorite theorem in all of mathematics. Everyone's got to have a favorite theorem. Actually, I guess the Pythagorean theorem, of course, is everyone's great favorite theorem. But beyond that classical result, Liouville's theorem is my favorite because it's such a deep result, leads to such beautiful mathematics, and yet is a theorem about how we can approximate algebraic numbers by rational. Well, with his beautiful result in hand, Liouville then considered the following number. I'm going to call it L. It's 1.11000, then a 1, then 17 zeros, then a 1, then even more zeros, and then a 1, where the number of zeros between the consecutive ones grows at a dramatic rate according to a specific pattern, which we won't worry about. Just think lots and lots of zeros, 1, even more zeros, and 1, and so forth. Well, this number has an endless list of rational numbers that approach it at an incredibly fast rate when compared to their relatively tiny denominators. For example, notice that the rational number 1.110001, which equals 1,110,001 divided by 1 million, is within nearly 1 over 10 to the 24th of Liouville's number L. So that is incredibly close to Liouville's number with a denominator of only 1 million, and you're within 1 over 10 to the 24th power. Well, it turns out that we could apply Liouville's theorem to conclude that these amazing rational approximations with relatively small denominators are too close to L to allow this number L to be an algebraic number. They contradict Liouville's theorem about algebraic numbers. Hence, L must be transcendental. Transcendental numbers do exist. This was, in fact, the very first number shown to be transcendental, and it's now known as Liouville's number. And in general, numbers that have amazing rational approximation of this sort are now called Liouville numbers. Well, Liouville found the first transcendental number in 1844. Nearly 30 years later, in 1873, the French mathematician Charles Hermite proved that E is transcendental. And by 1882, the German mathematician Ferdinand von Lindemann proved that pi is transcendental as well, as was conjectured for eternity. Now, the methods to prove these numbers are indeed transcendental are extremely complicated and technical, even more complicated than Liouville's theorem, if you can imagine such a thought. Although they all have the same first step. Assume the number in question is algebraic and arrive at a contradiction, a logical fallacy. That's how all these proofs in transcendence move forward. Well, in David Hilbert's great address at the dawn of the 20th century, offering the major open questions of mathematics, he asked if 2 raised to the square root of 2 power is transcendental. More generally, he asked if we are given algebraic numbers alpha and beta, such that alpha is not equal to 0 or 1, and beta is some irrational algebraic number, then is alpha raised to the beta power always transcendental? Hilbert actually wrote about this question. It is certain that the solution of these and similar problems must lead us to entirely new methods and to new insights into the nature of special, irrational, and transcendental numbers. Well, much to many people's surprise, only 34 years later, this question was answered by the work of the Russian mathematician Alexandro Gelfand and the German mathematician Theodor Schneider, who independently proved that such numbers are always transcendental. So in fact, the answer is they always are. Algebraic raised to an algebraic power, as long as the base is not 0, 1, and the exponent is irrational, that will always produce a transcendental number. Well, just as in the previous lecture where we saw that irrational numbers dominate the world of numbers, here we just remark that it can also be shown that transcendental numbers are the norm. If we were to randomly pick a number, it's with 100% probability that we'd stumble upon a transcendental number, and with probability 0, we'd accidentally select an algebraic number. So we again see how the mysterious and foreign appearing numbers are in fact the dominant features in our universe of number, while the familiar numbers, the algebraics, are in fact the unusual and rare. Transcendental numbers are in fact the norm. Well, despite the fact that essentially almost all numbers are transcendental, many questions remain open. For example, is e plus pi transcendental? And how about e times pi? Well, most number theorists believe that in fact both are transcendental, but no one has a proof. In fact, I have some really surprising news. No one can even prove that these two numbers, e plus pi and e times pi, are irrational. Of course, we all believe that these numbers are irrational, and yet these numbers are so complex that we don't even know how to show they are not ratios. You can see our understanding of this particular new branch of number theory is very limited. Even though great minds have and continue to work in this area, questions abound.